Let's do a problem involving rotational energy. For this problem, I'm going to have a ball rolling up a hill. And we're going to use conservation of energy to solve this. The velocity of the ball down here at the bottom of the hill is 10 meters per second. The ball has a mass of 2 kilograms. And as it goes up the hill, 50 joules of thermal energy is going to be generated. And I want to know how high it'll go up the hill. That's my goal. So there's two moments in time I'm interested in. I want to compare down here to how high it gets. Those are the 2 moments of time, to when it gets to its peak, I should say. So let's do it where we look at those 2 points. So I'm going to have the energy at the bottom has to equal the energy at the top. Now at the bottom, we've got 2 types. Well, we don't have any potential energy, and there's not going to be any thermal energy, but there is going to be kinetic energy. But there's 2 types of kinetic energy. Okay. We're going to have the translational kinetic energy at the bottom, but also the rotational kinetic energy at the bottom. At the top, when it gets to the top, we're just going to have the gravitational potential energy and the thermal energy that's been generated. Now here, our formula for translational kinetic energy, that's 1/2 m v squared. Rotational is 1/2 I omega squared. Gravitational potential energy is mgh. And we already know the thermal energy it's generated, that's 50 joules. Now I can go ahead and put in other values. So here I'd put in v squared, I'd put in v, 10, and I'd square it, which is 100. Okay. 1/2 times 2 is 1, so this is going to be 1 times 100, so this is going to work out to be 100. Now for my moment of inertia, I said it was a ball, so that means I need the moment of inertia for a sphere. We'll say it's a solid ball, so a solid sphere. So the moment of inertia for that is 2/5 m r squared. And then I've still got my omega squared. Oh, I know the mass. We might as well take care of this. We know that the mass is 2. 2 times 9.8 is 19.6. Okay, now right here, you can see these 2's are going to cancel. I'm going to be left with 1/5 times my mass, which is 2. Now I don't know the radius, and I don't know omega squared, but we do know the following, that the velocity of an object is equal to the radius of the object times omega. This is the condition for rolling. This ball is rolling. So r omega is going to be the velocity of the object. And since this is r squared omega squared, that's going to be v squared. This is going to become 100 plus 1/5. And then I've got my mass. Write this down. And this is 1/5 mv squared. Equals 19.6 h plus 50. Okay, so 1/5 times my mass is 2, my v is 10, so this is 100, 100 times 2/5, which is 0.4, this is going to be 40. So this is 100 plus 40 equals 19.6 h plus 50. So this is obviously 140. I'm going to subtract 50 from it. That's going to give me 90. And then, of course, we just do the division. And I get that h is going to be 4.59 meters. approximately. But the point is, this is just applying the law of conservation of energy. We've got to set up, as always, we've got to set everything up, draw our picture. We're comparing 2 points in time, the bottom to the top. You got to recognize at those moments what energies are present. At the bottom, it was translational kinetic energy and rotational. And that's an important thing to recognize now. We have 2 different types of kinetic energy. We have 2 different types of potential energy as well, and we also have thermal energy. So there's 5 different energies you have to be thinking about when you're solving these problems now. You've got to say, okay, is this rolling? Because if it's rolling or if it's spinning, that's rotational kinetic energy. Is the center of mass actually moving? Well, that's translational kinetic energy. Does it have some y position other than 0, of course? Well, then there's gravitational potential energy. Is there a spring that is compressed or stretched? That's elastic potential energy or spring potential energy. And then, of course, was any thermal energy generated? But it's the same approach that we've been using to solve these kinds of problems.